Welcome back. Cartesian products. The term Cartesian product of sets is named after the famous French mathematician René Descartes. The ordered n tuple a1 through an, notice it's ordered, is the ordered collection that has a1 as its first element, a2 as its second element, and so on until an as its nth element. So that's what n tuple means. N tuple means you have collected elements, n elements in order. Two tuples are called ordered pairs. That is, a tuple with only two numbers, two elements, are called ordered pairs. Note that two n tuples, a1 through an and b1 through bn, are said to be equal if and only if a1 is equal to b1, a2 is equal to b2, so on, an is equal to bn. Definition. Let a and b be sets. The Cartesian product of a and b, that's denoted by a cross b, is the set of all ordered pairs a comma b, where a is an element of capital A, little b is an element of capital B. That is, A cross B, the Cartesian product of A and B, is the set of pairs A comma B such that A is an element of A and B is an element of B. Find the Cartesian product of A comma B, where A is the set little a, little b, and b is the set 1, 2, 3. So notice a is a comma b, b is 1, 2, 3. So what is a Cartesian product B? It is the set a1, a2, a3, b1, b2, b3. So you see, A cross B consists of pairs. In each pair, the first entry is from A, second entry is from B. So capital A has 2 elements, capital B has 3 elements, A cross B has 6 elements. What about B cross A? Order matters. Now we want to put in pairs where first entry is from B. That's it. All right. The Cartesian product of the sets A1 through AN, denoted by A1 cross A2 cross so on until AN, is the set of n tuples A1 through AN. A1 is in A1, A2 is in A2, so on, AN is in AN. We write that in short by saying AI is an element of capital AI. Okay, that is A1 cross A2 cross all the way until AN is the set of n tuples where A1 is in A1, A2 is in A2. So these are all conjunctions. For example, describe the set A cross B cross C where A, let's see, A is the set 1, 2, B is the set 3, 4, 5, and C is the set 10, 11. So describe the set A cross B cross C. Well, I could write it one element at a time, but let's try, right? First entry, so your tuples are going to, each tuple is going to have 3 entries each. First entry comes from A, second entry comes from B, third entry comes from C. First from A, second from B, third from C. First from A, second from B, third from C. First from A, second from B, third from C. You see where I'm going with this, right? First from A, second from B, third from C. First from A, second from B, third from C. So notice I have already received 1, 2, 3, 4, 5, 6 entries using just one. All right. Now let's try with 2. Well, what's going to happen? If you notice, all of this is going to repeat. Where did I go? Instead of first being 1, first should be 2. That's all the difference. That's your set right there. Okay. A cross B cross C. So notice 2 elements there, 3 elements here, 2 elements here. So in all, 2 times 3 times 2, that's going to be 12, and we have 12 elements. Likewise, how about the set A power 3? A power 3 is the set A times A times A, where what is A? A is just the set containing 2 elements, 1, comma 2. So what does that mean? This is equal the set of, you see you have 3 powers, so you are going to have 3 tuples. 1, 1, 1, 1, 1, 2, 1, 2, 1, 1, 2, 2, 2, 1, 1, 2, 1, 2, 2, 2, 1, and 2, 2, 2. This takes care of all the possible entries from A. All right. A subset R of the Cartesian product A cross B is called a relation from A to B. Construct an example of a relation from a set A to a set B. So let's take A to be 1, 2 and B to be 3, 4, 5. So R should be a subset of A cross B. All right. So R, we are just going to make up a few things, right? 1, 3. So the first entry should come from A, second entry should come from B, and it does. 2, 5. That's it. I don't feel like writing more. Well, that's a relation. Any subset of A cross B is called a relation from A to B. Okay? Using set notations with quantifiers. Here is a way to use a set while describing the domain of a quantified statement. For all x element of S of P of x. So, this P of x represents a predicate, or what do you say? A proposition, okay? propositional function, or there exists x from S with a proposition. What does the following mean? For all x element of z, x to the fourth greater equals 0. What does that even mean? I'll write it in English because that's written in logic, right? For every integer x, the fourth power of x is greater than or equal to 0. That's all we have said here. Okay? What does the following mean? There exists an C such that x equals. So that probably means complex numbers. There exists a complex number x such that x is the square root of -1. Okay, so truth sets and quantifiers. Given a predicate P and a domain D, we define the truth set of P to be the set of elements x in D for which Px is true. Truth set. Let's see an example. The truth set of Px is denoted by the set, all those elements from the domain such that Px is true. What is the truth set? Truth set of the predicate Px, which says x squared equals 2, where D equals the set of real numbers. Okay, so you are looking for the set of all those x in the set of real numbers such that x to the second power is 2. Well, which is what? It is square root of 2 and negative square root of 2. That's it. These are the only two numbers whose square is 2. These are the only two real numbers. Well, what is the truth set of the predicate? Let's see. The second example. X squared is -1. Well, you're looking for those elements from the real number such that their square is -1. Well, that's never going to happen. So it is the empty set. All right. Next. D is C. So now you want complex numbers. Instead of real numbers, Math BB, Blackboard, C. All right. So you're looking for those complex numbers whose square is -1. It is no longer this. It is I and -I. Don't forget -I. Right? So that's how you identify the truth set of a predicate Px. Alright, so that completes lesson 7. We'll continue lesson 8 in our next videos. Until then,